I want to talk about novel RSA assumptions. And this assumption is called a low order assumption. And the reason why they are interesting because they have applications in cryptography, namely VDFs, which stands for verifiable delay function. Yeah, so this is a joint work with my supervisor, Peter Burchi, and you can read the preprint of our work on ePrint. Yeah, so my talk consists of 3 parts. The first part, I just quickly want to mention and give a glimpse of these novel assumptions, namely the low order assumption and the adaptive root assumption. And then I just want to motivate in the second part why these assumptions are interesting, because they have cryptographic applications. So I need to introduce what is a VDF and an instantiation of a VDF, namely the Piechak's construction. And so the syntax of a VDF and how exactly Piechak created his own construction. And then in the third part, I will talk about mainly our work, because if I don't tell you the first and the 2 parts, then you will not understand why our work is cool. So what is this low order assumption and the adaptive root assumption? So the low order assumption was introduced by Bonnet, Bunz, and Fish 2 years ago. And it basically says that in an RSA group, or more precise in a group of unknown order, it is hard to find low order elements. So if I give you an RSA group or a class group, it should be should be really hard to find U and L such that U to the L equals 1, and the order of L is bounded by this polynomial 2 to the poly lambda, where lambda is the security parameter. Obviously, U should not be 1 or -1 because we trivially know the order of these elements. So if we don't restrict U not to be 1 or -1, then the adversary can trivially break this assumption. But if we exclude the 1 and -1, then the assumption says that this should be damn hard. Okay, so what's the intuition behind this assumption?
Sorry, one question. What is given to the adversary? What is
That,
the knowledge of the adversary?
Only the group, So yeah, like you have the RSA group, and you need
okay,
to
but in this case, the -1 is meaningless. So that the 1 is simply just the unit element of the group, and the -1 is something completely unmeaningful. So there is no -1 in the group at all, because that should be just here. Okay, but go on.
What do you mean that the -1 is meaningless? I mean, it's -1 mod n, or if we are talking about RSA.
No. If it's the group is given, typically the group is given by simply just the black box stuff, so that you can just have the product of 2 groups elements. You have the unit element, and you can just have the inverse, and that's it. In this case, there is no completely unmeaningful that having the -1, because there's no minus in the group. So that this simply just -1 is a element with second order element.
Yeah.
But typically this is not the case. So that in the group you have no. Okay. At least the question
I
is
don't
that can you find
understand this either. What if the group is like a prime order group with just no low order elements? Then of course it's hard to find because they don't exist.
Yeah, exactly. So I mean, in some cases, obviously this doesn't exist at all. Like for example, if you have an RSA group which is a product of the same primes, then this just doesn't exist. But if it exists, then the assumption says that it's hard to find. Okay, so let's just think out loudly whether this is a weak or strong assumption. So, why?
So do you know the order of the group?
No. That's the point. Like it's an RSA group or a class group, so you don't know the order of the group. Because if you would know, then you can factor. Okay, so it seems like a strong assumption, because if you see this one, then the order is bounded by an exponential function of the, so the order is bounded by an exponential function of the security parameter. So the adversary could output an order which is pretty high, like, right? And so it seems like a strong assumption in the first place. So anytime when I say like exponential low order assumption, I refer to this bound. So this is an exponential low order assumption because this bound is bounded by an exponential function of the security parameter. If this would be a constant, then I would just refer to it as a constant low order assumption, or yeah, you got the hang of it. Come on. So, but it also seems a weak assumption because if I give you, if we have a low order element, then it is just not obvious how we could factor, for example, the modulus. Obviously, if this order is eventually 2, so L equals 2, then it's trivial. Trivially, we can factor the modulus. But in other cases, it's not obvious. It's like it doesn't really give us immediately help or not obvious. So the question is like, how does this new novel assumption relates to other classical RSA assumptions? And we want to establish some connections here, right? And then this is the second novel assumption called the adaptive root assumption. In our work, we didn't really concern about this, but still in this talk, I would like to just give some high-level ideas or what we think about this assumption. So you can, if you know the strong RSA assumption, it's like a sibling of the strong RSA assumption, but it's an adaptive version of it. So given a random group of unknown order, the adversary outputs W, which should not be equal 1, and the challenger outputs a random, adaptively outputs a random prime, and the adversary now should be able to compute the L root of this W. And if the adversary manages to do so, then she won the security game. And the assumption says that this game is pretty hard. So, I mean, if you know the strong RSA assumption, then basically it's just an adaptive version of it. Obviously, so one quick observation is that the number of primes should be exponential in the security parameter, because if it's polynomial, then the adversary could just pre-compute stuff. Yeah, but this is the adaptive root assumption. And we have this RSA Assumption Zoo. So this is how it looks like. And these are the two novel assumptions on the left-hand side. And for example, we know very little. I mean, we know some connections about these assumptions, but not satisfactory. So for example, it's a long-standing problem whether the RSA assumption and the factoring are equivalent or not. It's funny because there was a paper by Bonnet like 20 years ago that RSA assumption and factoring may be equivalent. And then like 10 years later, there was another guy, can't remember the name, sorry. There was another article which said that RSA assumption and factoring might not be equivalent. So it's just funny. So we don't really know. Obviously the factoring implies RSA, but we don't know the other direction. And yeah, we have these new animals in this zoo. And yeah, so the strong RSA, first of all, I really like this paper. It's a position paper on cryptographic assumptions by Shafi, Goldwasser, and Kalai. And you should read it whenever you want to work with cryptographic assumptions. Like they are arguing what is a nice cryptographic assumption, what is not a nice cryptographic assumptions. So the RSA assumption, if you're not familiar with it, it says that given a public key, a public exponent, it is hard to compute E root, where E is this public exponent. And the strong RSA assumption is a stronger version of it when we allow the adversary to choose this exponent on her own. So, and the observation is that the RSA assumption is one search problem, and the strong RSA assumption essentially is a exponentially stronger assumption than the RSA, because it says that it's hard to compute roots for exponentially many exponents. So Goldwasser and Kalai says that such an exponential assumption is not that really nice. So it would be nice to avoid such assumptions. That's what they say in this position paper. And in this regard, also the adaptive root assumption is not a nice assumption because there are exponentially many witnesses. So like one question is, low order assumption is equivalent to factoring or not? What can we say about it? Then yeah, the adaptive root also seems like a hard problem, but it also seems like a weak assumption because it is interactive and there are exponentially many witnesses. So it's like a challenging thing to approach it. But still, let me just give some remarks on the adaptive root before we are going into deeper with the low order and the VDFs. So exponentially stronger than the RSA assumption, as we already said. And it's a T-search problem with exponentially many witnesses. Interactive assumption, in crypto, we don't really like interactive assumptions because it's hard to reason about them, or it needs a little bit more cryptographic machinery. And seems like a hard problem, but still we know very little about its complexity, so please help. It's like an interesting problem, and I encourage you to spend some time on it. And just to give an analogy, we have a similar result. So I mean, even though Goldwasser says that it's not a nice assumption, we saw something really similar in lattice-based crypto, because like the LWE is a one search problem, and it was reduced to the shortest integer solution problem, which is an exponential T-search problem. And this paper is like super famous by Oded Regev. So maybe, we don't know, but one could produce a proof which says that also the factoring is reducible to the stronger RSA or the adaptive root assumption, and then we would have a really similar result than the one to Oded Regev. Right? So we don't know, but it's possible that this is the case also for RSA groups. And again, this is an advertisement. If you want to read a nice paper, position paper, then I think this is a super nice paper by Goldwasser and Kalai. Okay, so why do we care about these novel assumptions at all? First, I mean, this is, I think, a cryptographic way of doing things. First, you create something which is cool, and then you ask the question whether it's secure. And this is exactly what happened. So there was a really nice protocol, really nice tool, cryptographic tool. And then we were asking the question whether it's secure. So there was no really an established theory behind it. First, there was just an applications. So a verifiable delay function, or VDF for short, is a function which has three probabilistic polynomial time algorithms: the setup and the evaluation and verification. And the idea is that it's basically, if you know time lock puzzles, it's proof of sequential work, but it's publicly verifiable with a succinct proof. Let me elaborate on that. So a setup takes a parameter, the security parameter, and the time parameter t, and produces public parameters, evaluation key and verification key. And the evaluation takes as arguments is the evaluation key and x from the domain of the function, and produces y and p, which is a proof. And the evaluation should not be parallelizable. So even if you have AWS, Amazon Web Services, or Google Cloud behind your back, you cannot evaluate it faster than an honest player. So the evaluation should not be parallelizable. It should be an inherently sequential function. And verification, on the other hand, should be really succinct. So given the verification key and x and y and the proof, anyone basically should be able to really fast, in a fast manner, should be able to verify that the function evaluation was carried out correctly. And what we even more demand from this VDF is that there should be an exponential gap between evaluating the function and verifying the function. So if evaluating the function takes t sequential steps, then verification should take ordo log t, which is like pretty difficult, you will see. So it's really challenging to create VDFs. Obviously, what are the security requirements? We want correctness. So if there's an honest player who evaluates the function correctly, then it should be able to always convince the public. And obviously, which is more challenging, we also want soundness. So if there's a malicious function evaluator, it should only be able to convince the honest guys with a negligible probability if she's lying. And we also want that the evaluation of the function should not be able to parallelize maybe class groups. So I mean, class groups is another group of unknown order other than the RSA groups, but it's not clear whether class groups, the group operation in class groups is parallelizable or not. So please, dear mathematicians, help. And yeah, there should be an exponential gap between the time complexity of evaluation and verification. So like one question you might ask, like a trivial idea would be to just iterate a cryptographic hash function. Is it a VDF? You cannot, if it's collision resistant, then you cannot evaluation is trivially sequential. But the question is how you verify it succinctly, because the trivial idea would be that then also the verifier should just recompute the whole hash chain, but then in that case, the verification algorithm would have the same time complexity as the evaluation function. So you can do this with snarks, ZK snarks, or ZK starks, but it's a little bit involved. For that, please refer to the original paper by Bonnet et al. So you can have some proto VDFs, let's say, but it's not a nice, not that nice construction. So you can have a VDF with hash function and ZK snarks. Okay, so why people are excited about verifiable delay functions? For example, it allows cool things in cryptography, like non-interactive timestamping. So I could prove to you that I was ready with these slides 3 days ago in a way that I give you the PDF and I give you a proof that I evaluated a VDF on the hash of these slides, and it took me to compute this VDF 3 days. And then since you are sure that I cannot compute the VDF faster than 3 days, then you will be sure that indeed I was ready with the slides 3 days ago, and I didn't do this just 10 minutes before we started the call. So it allows to do non-interactive timestamping, randomness beacons. Randomness beacons, it's a cryptographic source of entropy, unbiasable entropy. So you can think of like a beacon which emits pseudorandom numbers, unbiasable pseudorandom numbers, like every hour or so. Yeah, for more details, please read the paper by Benedict Bunz et al. It allows us to do proof of replication. So I could prove to you that I store a file not just once, but like 3 times or 5 times. So I replicated honestly your data. So for example, you want to outsource the storage of your family photos to Amazon, then Amazon could prove to you that it does not only store your family photos in 1 copy, but in 5 copies. And this construction also relies on VDFs. And we can also create novel consensus algorithms. Yeah, this is a paper by Cohen and Pieczak. Okay, so there are many cool applications, and the question is whether it's secure. So the main question is like the soundness of these protocols. And okay, so why do we need groups of unknown order? This is like the first question. So let's say we have a group G, and we raise G to the 2 to the T. T is the time parameter. T is usually like 2 to the 30, 2 to the 50. And the output of the function is H. And since we cannot, there's an assumption that we cannot parallelize repeated squarings. we cannot compute this faster than t squarings, right? This is not the case if we know the order of the group. Why? Because suppose we would know the order of the group, then the evaluation would be super efficient. Because then you can reduce this exponent by the order of the group, and then it's trivial to compute the evaluation function, the evaluation algorithm. Okay, so recently there was another nice paper that said that we cannot have delay functions without instantiating them in groups of unknown order. So we either need RSA groups or class groups, but we know very little about class groups. It's not even clear whether the group operation is parallelizable or not. And recently on ePrint, there were new articles about elliptic curves, which has groups of unknown order, but it's pretty novel. I'm not that familiar with those results, but generally they say that we have two types of groups of unknown order. Okay, so let's see an instantiation in RSA groups. Let G be a finite cyclic group with generator G, and the public parameter is the group itself. So like it's just a modulus in most cases, and the hash function. And the evaluation is just, we hash the X, the domain. So we have X in the domain and we just hash it and do this repeated squaring T times. And the main question is, how can we verify efficiently in ordo log T that this evaluation was carried out correctly, right? There's a nice video, it's on YouTube. It was recorded last year at Stanford by Dan Bonnet. But let me quickly describe the protocol of Piecek. It's really nice. So it's a recursive protocol. And obviously, so we want to basically check membership in this language, whether we have, so we have G, the group, little g, h, and t. And this is the statement we want to verify. Obviously, if G and H are not in the group, then we just reject and stop. If T is 1, so this is the base case of the recursive protocol. If T is 1, then the verifier can just do trivially this small exponentiation, this small squaring in the group. If it holds, then accept, otherwise reject and stops. So this is not that, I mean, it's trivial kind of. The main challenge is how to make the recursive step. Okay, so this is a really nice idea, and yeah, I just love it. So let's say the way we prove it is that we take this middle element denoted as V. So the middle element is, if you want to go from G to H, then this is the middle element because V equals G to the 2 to the T half. And we send this to the verifier. The verifier checks whether this middle element is in the group, and if not, then we stop. So what do we need to check? We need to check whether V to the 2 to the T half equals H, and simultaneously we need to check that also G to the 2 to the T half equals V, right? Because then this would prove that indeed G to the 2 to the T equals H. But the thing is that now, instead of just proving, so it seems like we are at square one, because instead of proving one equality, now we need to prove two equality, right? So it's like we screwed it up. But no, because here we have the same exponent, luckily, so we can verify this. It's like a classic trick in crypto. So since these two equalities have the same exponent, we can just verify them simultaneously by checking a random linear combination. So the verifier sends an R randomly sampled from this set, and then we can just check a random linear combination of these two equations, right? And okay, so let's denote G1 as, and this is why it's nice, because then we see a recursive pattern emerging. Because if we call G1 as G to the R multiplied with V, and H1 as V to the R multiplied by H, then what we now need to prove is that this tuple is in the element, right? So we just recurred on t half now with G1 and H1. So this is why this protocol is nice, because this protocol is logarithmic in t. So we achieved what we wanted. And the proof is also really small because it only contains log t elements, log t v elements. Is there any questions so far on this protocol, or shall I continue? Now it's the time to give comments, questions, if you have any. If no, then I continue. Okay.
Just please wait a sec. I need to process the new information.
Right. I mean, just shoot any questions. So in the beginning, it seemed that we screwed it up because we had two equations we needed to prove, but luckily, since they have the same exponent, we can verify them simultaneously. So we sample a random R, and obviously this is the interactive description of the protocol. It can be made non-interactive with the Fiat-Shamir heuristic. Right, so instead of relying on the verifier, sending the random R's, the prover can just generate it themselves, right?
Okay, I'm fine. Thanks.
So it's a nice recursive protocol. We love it. It's beautiful. But what can we say about the soundness of the protocol? And so the correctness is kind of trivial. It's not that important. It holds. So what can we say about the soundness of the protocol? And that's where the low order assumption comes into play. Surprise, surprise. So let's say we can break the low order assumption with this bound. So let's say we have an adversary who can break the low order assumption, and this means that it outputs an element U with order L, where L is less than 2 to the poly lambda. And now I'm showing, or I mean, Bonnet et al. Showed in their paper that how can this attacker potentially break the soundness of the Piaczek protocol. So given that a correct evaluation of the function, the malicious prover can create another incorrect tuple, but it will be incorrectly accepted by the verifier with probability 1 over L. Remember, L is the order of the low order element. Let me show you. I mean, it's just a quick computation. You can check it by hand, but this is a true statement. So malicious prover sends V, which is a lie, because now we also multiply G to the 2 to the T half with an element U, with this low order element. So why is it a problem? Because the soundness of the argument system doesn't hold whenever the randomness plus 1 is congruent to 2 to the T half mod L, because then this, I'm going to show you this, so don't worry if you don't understand it now. Because then in the recursive protocol, this tuple will be accepted. Why? So we need to check whether G to the R to the V raised to 2 to the T half equals V to the R multiplied by H times U. So basically this is what we are stating. And this is true because now let me just put in the place of V this quantity. So this is the same, but now I put V here and there. So since G to the 2 to the T equals H, those are vanishing. So at the end of the day, if we cancel out what should be canceled out, then what we will have is U to the 2 to the T half equals U to the R plus 1. And this holds whenever R plus 1, so remember U is the low order element, it has an order L. So this holds whenever the exponents are congruent mod L. So if this is a low order element, then the prover is really happy, because then he can just cheat with probability L. This is the main observation, how how a low order adversary could break the soundness of the PHX VDF. Okay, and so let me repeat. Soundness of the argument system doesn't hold whenever R plus 1 is congruent to 2 to the T half mod L, since this tuple is incorrectly accepted by the verifier. Okay, and the Bonnet, Benedict Buens, and Ben Fish says that this happens with non-negligible probability. So remember, this is not true because the low order is bounded, lies in this interval. So an observation is that there might be weird adversaries who is only able to break this assumption where the low order is close to this bound. So then we will have weird adversaries who can break the low order assumption, but still breaking the soundness of the PHX protocol would be negligible. So put it more formally, we might have adversaries who can only break the low order assumption with their order being in 2 to the theta polylambda, and then the probability of breaking PHX protocol would still be negligible, because it would be 1 over 2 to the theta polylambda. So this is like an observation that it seems that the original definition of the low order assumption is too strong. This was kind of like the starting point of the paper. That I mean, this was not the starting point, but an important observation that it seems that the original definition of the low order assumption is too strong. And then a natural question is that, okay, so it would be nice to, so we see that the original low order assumption with this 2 to the polylambda bound is too high. So then the question is, so the original definition of the low order assumption is a non-necessary assumption for breaking the soundness. So then the question is, what is the weakest low order assumption which is necessary and sufficient to break the soundness of the protocol? And yeah, okay, so I was a little bit hand wavy here. So this is enough, because there are non-negligible phi n having factors in 2 to the polylambda. So there indeed might be adversaries who can be only specialized in finding these kind of low orders, because these low orders are indeed non-negligible. Okay, so this imprecision gives us ways to improve on this bound. And what we found is that super polynomial low order assumptions are sufficient. So this is exactly the same low order assumption definition, but here we don't have an exponential function of the security parameter, but a sub-exponential. And then, okay, let us be greedy, because now we decreased from 2 to the polylambda to 2 to the sub-exponential. Then can we decrease it to polylambda? It would be nice, or constant, like let's be super greedy. Let us dream big, right? And it turns out that in that case, the assumption would be not sufficient. So it's kind of a technical proof. So what we need to do is we need to now prove that this sub-exponential low order assumption is indeed sufficient. How do we do that? With the forking lemma. Basically, we almost do exactly the same technical proof what was done by Bonnet et al. In the survey paper. A little bit of tweaking. And we can't assume polynomial order assumptions, at least not, we cannot prove the sufficiency with the forking lemma. because at the end of the forking lemma, we will have a quantity like this. So epsilon squared divided by t minus epsilon divided by f lambda. Let f lambda denote the bound, the function of the security parameter which bounds the order of the low order element. So the thing is that if f lambda is a polynomial, then this term would be non-negligible. So then we cannot prove, at least not with the forking lemma, that this polynomial low order assumption would be necessary, would be sufficient. Okay, so we need to be satisfied with this sub-exponential low order assumption. And then, okay, so the next step is now we established this kind of minimal. We still don't know whether this is a minimal or the weakest assumption we can have. Let's establish the relationship between the sub-exponential order assumption and factoring. Okay, so it seems that f lambda needs to be super polynomial, but we don't know. If you can prove that f lambda is enough to be polynomial, then it would be nice, because then our reduction would work in that case. So because our reduction would say that the polynomial low order assumption is equivalent to factoring. I will show it in a second. Okay, so what we had a lemma or a theorem, let's say, that if we have so we can prove a partial reduction of the super polynomial order assumption and factoring, from factoring to the super polynomial order assumption. So let b be a fixed integer. The factoring assumption is reducible in polynomial time to the low order assumption for RSA moduli. So not all RSA moduli, but only for those moduli when phi of n has no prime factor between in this interval between b and 2 to the poly lambda, and moreover the GCD of p minus 1 and q minus 1 equals 2. So you might say, wow, this seems like a super artificial reduction. But in the paper, we argue that it's not, because in most of the cases, at least in practice, low order RSA moduli have this structure. For example, OpenSSL generates RSA moduli in a way that it ensures that p minus 1 and q minus 1 has no small factors. So in most cases, we have this kind of structure. So it's not like a super crazy assumption to have for the RSA moduli. Okay, so let's prove the opposite, namely that if we would have an efficient adversary who breaks the super polynomial low order assumption, then it would be able to factor a non-negligible amount of RSA moduli of this kind. So we have A who breaks the low order assumption with 1 over q lambda. Q is a polynomial of lambda, so it's with A can break the low order assumption with non-negligible probability. And now we would like to we devise an efficient adversary B who can factor non-negligible fraction of random RSA moduli by using A as a subroutine. How do we do that? Right, so our adversary A gives us a pair U and L such that U to the L is congruent 1 mod n. And the order of this element lies between 2 and 2 to the poly lambda. I'm proving this with the exponential low order assumption, but the reduction trivially works also for the sub-exponential. Right, so this is kind of the main observation of the reduction. So if we have this low order element, then the low order element is, so you can think of this RSA group as as a direct product of ZP star and ZQ star. Hence, the low order is an LCM, least common multiple of the order of PU and order of QU. Obviously, the problem is that we don't know P and Q, but we don't need to know. That's the main observation. So the idea is that whenever these two quantities are not equal, then adversary B could factor the modulus if L is smooth enough. Okay, so now a lot of uncertainties, bear with me, I explain everything. So why is this the case? Because, so let's imagine we have this U and L, and what we want to do is we want to recover all the prime factors of L, of the order of the low order element. Why? Because B could raise U to the power of L divided by R for all prime factors R of L until modulo one prime factor of N, but not the other, the order of U divides L divided by R, which can be detected via this this GCD. So the main idea is that if we know all the prime factors of L, then we will be able to recover one of the non-trivial factors of N just by testing this GCD. This is the main idea of the reduction. So now we need to establish two things. The first thing is that what's the probability that order of order PU does not equal order QU, and it's kind of easy because so we want to find prime factors where this cannot be the case at all. This holds whenever P minus 1 divided by 2 and Q minus 1 divided by 2 does not have any common factor at all. And this is basically kind of like if you would generate two random numbers and they don't have any factors at all. And so basically it's the probability of coprimality of random integers, which is kind of an established thing. So we know that the probability of coprimality for random integers is 1 divided by zeta 2, which is approximately 2 to the 6 divided by p squared. So it's a constant, we doesn't really care. So with constant probability, we have that for random prime factors, this GCD equals 2. So let's examine these two cases. Order PU and order QU cannot be 1 at the same time because by the definition of the low order. And if it's 2, then we can factor trivially. It's like I think every kid knows, even in the kindergarten. So to show this is homework, or you can read it in our paper, but it's kind of a standard fact. So we can assume that with constant probability, this holds, that order PU and order QU are different. Okay. So now what we need to find is that what's the probability that we can factor out that L is smooth enough to, remember, we want to factor out all the prime factors of L and check the GCD. So we want to find all of its prime factors in a brute force manner, but still in polynomial time in lambda. So what we just do is that we try to recover all the prime factors below this bound B. And we hope that all the prime factors of L will be less than this bound B, right? So what we do is just, we find the smallest factor, we raise it till we can. We raise it till A1, which is the maximal exponent, which divides L, and then we iteratively continue. And hopefully, let's hope that all the prime divisors of L is smaller than B. If this is the case, then we won and we could factor the modulus. So now we need to establish the probability that what's the probability that we will have that for a random RSA modulus, we will have such a nice modulus that in that case, L doesn't have large factors. And there's a really nice theorem by Gardner, and it says, I will not state the theorem now. It's a beautiful theorem from number theory, analytic number theory, and it says that basically the integers up to n, which doesn't have divisors in this interval, are really a lot. So there's a so this is a function gamma. Gamma denotes a function which counts all the numbers smaller than 2 to the s lambda. 2 to the s lambda is basically the modulus we care about. And we want to count the number of numbers less than 2 to the s lambda, which doesn't have any prime divisors between b and 2 to the poly lambda, right? And using Gardner's theorem, we can establish this portion, and this portion is luckily non-negligible in lambda. So we are super happy because with non-negligible probability, we will have a nice modulus. And so at the end of the day, we will have that we can factor using our lower order adversary with this probability. The first term is a constant, the second term is 1 over a polynomial, and also the third term is just a polynomial squared. So we can factor with non-negligible probability. Right. So and observe that here we can exchange 2 to the poly lambda to essentially any super polynomial bound. So this reduction works for the weaker low order assumptions as well. Right. Okay. Any questions on the reduction? Because now I'm switching to the last part, which is quite a small part, but still, I think it's a cool application of a zero knowledge proof system by Sharon Goldberg. So if there's no question, then I move to the last part. So okay, it seems like everyone understood everything. Cool.
No, that's everything is tight enough. Okay, just go ahead. Thank you.
So like it would be nice if, like, let's say so let me go back. So I didn't say any single word about like this. So how we can generate such an RSA modulus? Because if like, let's say you trust me and I generate this RSA modulus, then obviously I will know the factors of this RSA modulus, and then whoever knows the factors of this RSA modulus can just generate any fake proofs. So we need to have like a multi-party computation, a distributed RSA multi-party computation to generate the modulus in a way that none of us will know the underlying factors of the modulus, but still we can be sure that that integer is a semi-prime. So, and it would be nice to, for example, certify this integer, that this integer is free of low order elements, because then we can be sure that we can safely use this VDF. So either this setup is a trusted setup to generate this RSA modulus, or we can create a distributed way to generate this modulus. So that's and how can we certify? And the question is now, how can we certify? So how can we certify integers that so I can prove to you that an integer does not contain any low order elements. And for that, we use a result by Goldberg, Sharon Goldberg from Boston University. So there's like a lemma which says that if we have this map, x to the e mod n is a permutation if and only if e is co-prime to phi of n. Okay. And in this paper, which is quite a cool paper by Goldberg et al., they show a zero knowledge proof system for this very language, what we need. So using Sharon Goldberg's proof system, we can prove that an RSA modulus and has, so given E and N, it this equation holds, like the GCD of E and phi n equals 1 without leaking any information whatsoever about the factors. Why is it good for us? If we generate E in a way, so let E be the product of primes up to, so let's say I want to prove to you that the RSA modulus is free of low order elements less than B, where the order of the low order element is less than B, then I can just create a E, which is the product of odd primes up to Pn. Pn is the largest prime smaller than B. Then I just need to take n and this particular E, and I can prove to you, given this lemma, that my favorite RSA modulus doesn't have any factors smaller than B. Yeah, so this way I can just use this HVZK, honest verifier zero knowledge proof system by Goldberg to certify RSA modulus that they are free of low order elements. And this is super nice because it's a really lightweight proof system. So let's say I have a modulus 1024 bits, and my security parameter is 80 bits, and I want to prove to you that it doesn't have low order elements smaller than 2 to the 10, then the proof size is, the certification is just 6.4 kilobytes, which is super lightweight. And the nice thing is that the size of the certification only depends on the security parameter, of the zero knowledge proof system. So it only depends on the soundness error you want to admit. So generally the proof contains lambda divided log 3 group elements and requires the same amount of modular exponentiations, which is for 80 bits soundness error, it's like 50 modular exponentiations, and 50 modular exponentiations, you can do it in a distributed RSA generation setting easily. So the observation is that when we generate such an RSA modulus, even if we don't know the constituting prime factors, we can certify this integer, this RSA modulus, that it doesn't have any low order element. Nice. And so this was just a short paper. These were our only contributions, but there are still many open problems. So like maybe I don't know, someone can come up with a someone can come up with not a partial reduction but with a full reduction. So maybe the sub-exponential low order assumption is equivalent to factoring, who knows, please help. Would be nice to establish a necessary and sufficient assumption for proving the soundness of the PHX protocol. Note that our sub-exponential order assumption is still not necessary. It's a subtlety, but it's still not necessary. If there's a question regarding that, I can elaborate on that. Yeah, and like a big question nowadays is that the adaptive root assumption is a secure assumption. I personally find it a little bit a difficult problem, but it's hard to reason about it because it seems like a weak assumption, but still. And how does the adaptive root relate to factoring, strong RSA? Is there any special purpose algorithm which breaks either low order or the adaptive root assumption and is asymptotically faster than the fastest known factoring algorithm? So is there any, basically the main question is that, is there any special purpose algorithm which can find low order elements or can break the adaptive root assumption without factoring the modulus? And the nice thing is that if you could answer any of these questions, then you can claim some cash. There are some bounties on these questions, so you should visit this website and you can check them out. I really encourage people because these are nice problems. And yeah, these are the references I was talking about. And yeah, there were 4 people who were helping us a lot, and thanks for them. And yeah, thanks. Any questions?
Yes, thank you. Wow.
So can you say something about the necessity of your assumption?
Right. So the thing is, so it's still a non-necessary assumption. Why? Because so you see this sub-exponential bound, and if you pick a polynomial between the polynomial and this guy, this sub-exponential function, there will be still an adversary who could only break the low order assumptions for orders being really close to this sub-exponential function. And in that case, this sub-exponential low order assumption would be still broken, but the probability that it breaks the PHX soundness is still non-negligible. Still negligible. So that's the reason even this sub-exponential low order assumption is non-necessary. But if you decrease this bound to a polynomial, then you can't prove the sufficiency of the assumption. So it's like there's a tension, a really great tension between this bound. You can't decrease it because then you can't prove that it's sufficient. And yeah, if you increase it to sub-exponential, then it's not necessary. And the thing is that the forking lemma only allows us to prove the sufficiency for sub-exponential low order assumptions. And the nice thing would be if any of you could prove that you can decrease this bound to a polynomial function of lambda, then our reduction would instantly prove that the polynomial low order assumption is equivalent to factoring. So that's the reason we still cannot really be sure whether it really holds, the sub-exponential low order assumption really holds for all RSA modulus, but at least we can prove, we can certify RSA moduli that they are free of low order elements. So in practice, one can still be certain that the modulus it's using, it's kind of safe.
So is the use of the forking lemma kind of the barrier?
Yeah, I mean, the barrier in the sense that if you are proving sufficiency, then and you use the forking lemma, then that's the maximum you can bring out of it. Okay. So maybe if you are proving the sufficiency with some more elaborate techniques, with some other deeper tool, then maybe you can prove it to polynomial bound, but I don't know, maybe some other more clever people can do it, but we were not able to do that.
Okay, thanks.